Hi, I like Picross, so I made one in Minecraft. In case you don't know what a Picross is, it's a type of puzzle where you're given an empty grid and a bunch of numbers on top and to the left. Some of the squares in this grid are supposed to be filled in, and the rest are supposed to be not filled in. And your goal is to fill in all of the supposed to be filled in squares using the numbers as a guide. Each number represents a group of that many filled squares in a row or a column. And if there are multiple numbers correlating to a single row or a single column, that means there are multiple separate groups. The order of the numbers does matter. So for this example, there's a group of 1 and a group of 3 in the middle row, with the group of 1 being somewhere to the right of the group of 3. When translating a Picross puzzle into Minecraft, I had to decide on a few things. First was what size of puzzle I wanted. I chose to go for a 5 by 5 grid, mostly because it's not that big and its dimensions are both multiples of 5, which I like it. After this was how I would go about accepting player input. I was originally going to have the player shoot target blocks with a bow, so you're going to notice a lot of target blocks on the front end of this, but later on I added buttons so you could throw wind charges instead. I figured this would be handy because they fly in a straight line, so it's easier to line up your shots from a distance. That way you don't have to, fly around trying to shoot all the target blocks. I kept the target blocks, though, since they didn't break anything, and they helped make it more obvious where to shoot. I also had to think about back-end stuff, like how I would handle data so I could move it and mess with it and stuff, but I'll talk about all that as it comes up. Now to actually start designing this massive behemoth, I figured it would be a good idea to break it up into a few separate pieces that I could reuse repeatedly, kind of like functions in programming or Lego blocks. Then I could string together all of the individual parts, hook it up to a front panel with inputs, and boom, job's done. Because of this blueprint, for each part I designed, I was limited to a 7 by 7 footprint on the front, and I could pretty much just use up as much space as I wanted going backwards, but I had to limit myself to 7 by 7 in some dimension. Otherwise, things wouldn't fit together nicely and they would get in each other's way when put into the full thing and all that stuff. The first individual part I worked on was just like the individual cell module thing. So the thing that would represent the individual squares in the grid. I tried to color code everything too, so all of this is going to be in the light blue. I knew that each cell would need to have 3 states, being blank, crossed out, and filled, so I started with that. Eventually I ended up with this thing, which I've split up to help me talk through it. First is the display. I needed to be able to display which state the cell was currently in, so I set up a big light panel and hooked it up to a couple of composters. If the back composter was pushed up by the sticky piston below it, the cell would be considered filled and the entire light panel would light up. If the front one was pushed up instead, it would be considered crossed out and only the light in the middle would turn on. Usually cells like this are represented with an X in normal Picross, but that would be really annoying and I figured this got the message across just fine, so I went with it. Finally, if neither of the composters are up, the cell is considered blank and the display goes all dark. After getting that all set up, I had to think about the logic of switching between these states. I set up 2 inputs, one for toggling whether the cell was filled or not, and one for toggling if it was crossed out. The main problem I had was that I wanted to be able to overwrite one state with the other, while still being able to turn it back to blank if the input matched what it currently was. So, if the cell was crossed out and you try to fill it in, it would change its state to be filled, and if you try to fill it in again, it would reset to the blank state. Basically, I wanted logic to follow this chart, where the squares are the different states and the arrows show how the state changes based on the current state and any input received. Eventually, I got this design figured out, where each input would send a short pulse to the corresponding composter's piston, and a slightly longer pulse to the opposite piston. That way, the right side gets toggled on or off, and the opposite one always ends up off. Finally, having two inputs for each cell sounded like it would be really annoying to work with as a player, so I wanted to set up a system I could use to change whether I'm setting the cell to crossed out or filled. Then I would still be using two inputs, but one of those inputs could be shared across all of the cells, basically acting as a toggle between fill mode and cross out mode. That's what this lime green stuff ended up being. If the lime green is on, you're setting to crossed out, and if the lime green is off, you're setting to filled. This part wasn't too hard since there was just enough space on the side to just slot in a few torches and some pistons to control where the line gets a signal. And that is the individual cell done. Thankfully, I could build up a giant frame, and because I was conscious of how much space this thing would take up while I was building it, I was just able to use the /clone command to copy this single one into each of the 25 places I needed it. Thankfully, thinking ahead can save a lot of time. After I finished all the cells, I hooked up all of their lime green toggle lines to one big toggle to control all of the individual ones. This wasn't difficult at all. I just had to put down some lines, pick a place for the big toggle to go out front, and hook up a display for it to show what mode it's currently in. For the display, I basically just copied over the one I used in the cells. This lectern here is to give the display a minimum signal strength to make the dot in the middle show up when it's not in the fill mode, since the state you're toggling to is just stored as a binary on-off signal. While I was setting this up, I figured it would probably be handy to have a button I could use to conveniently reset the board instead of needing to go through cell by cell, changing each one to blank manually. That's why I put in these red lines. They just give an extended pulse to both comparator pistons, meaning when the reset pulse ends, both composters end up retracted and the cell is left in the blank state. This also wasn't super hard, I just had to figure out a way to do that without messing up any of the logic already in place, which this repeater dust combo does quite well. The next thing I wanted to add was a system for detecting if you've solved the puzzle by filling in all of the cells that were supposed to be filled, and either leaving all the cells that are supposed to be empty blank or crossing them out. When I was thinking about how I would do this, I noticed I had conveniently put the composter for the filled state at the back of each of the cells. This was pretty lucky because it meant I could access it easily to check whether each cell was filled or not. Keeping this in mind, I also needed a way to specify what the intended solution was for the puzzle. It would be really annoying if you had to rebuild massive sections of the redstone if you wanted to change what the solution to the puzzle was. So I opted to add a bunch of copper bulbs you could toggle to set whether each cell was part of the solution. Then I came up with this little system in yellow to see if the current state of the cell matched the intended state. Each cell got one of these, and I fed all of those into a line where if any of the cells were wrong, it would turn off this win indicator line. All I had to do after that was hook up the indicator line to a big light, pop a little symbol on the front end, and after some bug fixing, the win indicator was all done. Now, at this point, I was fairly content with what I had made. You could put in a puzzle, mess with each cell on the front end, and the machine would tell you if you solved it correctly. Sure, you would need to put in the numbers manually when you're setting the puzzle, but that would be really hard to do automatically with redstone. I didn't even know if it would be possible with the space limitations I'd set for myself. I was ready to leave it as is. Of course, if you've been paying attention, you know that this is not where I stopped. There's more time left in the video, there are two colors in the redstone I haven't even mentioned yet, and quite notably, the numbers in the final thing are not just hooked up to a bunch of levers. I figured I would at least give it a try, and in the end, I was able to figure out some stuff and be quite proud of the results. To start the hard stuff off, I knew I needed a way to display a number. As such, I turned to my typical solution for such a problem, the 7-segment display. Unfortunately, I am too stubborn to just copy a design from the internet, and while I did have a few designs already cooked up, scattered around my creative world, they were all too big. I needed one that fit into a fairly limited space so that multiple of them would fit side by side, bottom to top, without breaking, like I mentioned earlier. This is where the 7 by 7 limitation really starts being difficult. Unfortunately, for a while I wasn't able to make one based on my previous designs. They were all too big and bulky to compress into the space I needed. Because of this, I took a look to the internet to see how small someone's got one before, maybe get some inspiration, try to think about how to do things a different way. Luckily, I was able to come across a Reddit post by someone going by the username Palco Japan. I think maybe that's how you pronounce it. I do not know. I'm sorry if I screwed that up horribly. But this person was showing off a pretty small 7 segment display. I'll leave a link in the description to the post. It used pistons to push composters in front of comparators to turn on the segments, similar to what I was doing with the state changing with the cells. Thing is, up until that point with the 7 segment display, I had only been using copper bulbs, since that was what I was used to for my previous forays into the land of 7 segment displays. Unfortunately for me, copper bulbs can be pretty limiting on where you can power them from, since you need to use an adjacent block. They also worked best if you are working with observers, since they toggle every time they're powered. The piston suggestion was really helpful in this regard, since pistons would give you more options to power them from by making them point in all sorts of funky directions, and they were able to react directly to input power by just extending and retracting. Unfortunately, I couldn't just study this design, breaking down each and every component of how it worked until I made a near exact copy, and this was for two main reasons. First, like I said already, I can be very stubborn. I didn't want to copy a design off the internet. I wanted to make my own, at least to some extent. Second, though, is the actually like practical one. It wouldn't work like I needed it to. It took a lever input in a specific spot to set what number it was displaying, and based on some of my own forethought into later steps of the Picross, I would want my numbers to display based on a signal strength input. Now, I could mimic the input it wanted by using a red coder and some pistons to do some stuff, but that addition would make it too large to fit properly into the space I needed it to. Even with the problems, though, just seeing that it was possible to make a 7 segment display this small and getting the suggestion of using pistons instead of copper bulbs, that was enough to help me make some progress. So, I went back to the drawing board, I set up a chart of what numbers needed which segments, and I looked for patterns. At some point, to make things easier on myself, I realized I didn't need any numbers higher than 5 because this was only a 5 by 5 Picross. So I just left them out. And after a bunch of wiring, testing, and rewiring, I came up with this. It is a complete mess, but it works. It fits into the space I need it to. It's almost perfect. I only had one issue with it, and that is when you passed it a signal strength that it didn't know what to do with, it defaulted to displaying a 9. This is because all of these segments were on by default, and specific numbers would just turn them off as needed. The fact that it looks like a 9 is a coincidence. This is unfortunate because I wanted them to be blank when they're not needed, and seeing a 9 on a 5x5 Picross board would be pretty confusing to anyone playing. To fix this, I jumped right back into the development process. I cloned what I had, so I had a backup in case things went horribly wrong, and I started just tearing in, dismantling, rewiring, changing, trying to make it so that all the segments were turned off by default and the numbers turned them on as they needed. It was tough work, though. And before I got too far into it, I had a different thought. What if, instead of keeping them off by default, I just made them turn off? I could use the design I already had, make some minor tweaks, add some extra redstone, and forcibly turn those segments off. With this plan in mind, I left what I was doing, made another clone, and started again. I didn't break anything this time, though. Instead, I looked at which segments I needed to turn off, and I looked for ways I could do so. That's how this white line was added, what I called manual override. This powers all of the lines that turn off the individual segments of the 9, meaning whenever the input signal was out of bounds, I could separately activate the manual override, and the display would be blank, just like I wanted. Now I needed to work out the logic of how I would work out what numbers go where, starting with the rows because I figured it would be easier. As I mentioned, I had been thinking about this and how to do it for a bit. I figured I would have to do some addition, which is why I was leaning towards using signal strength to carry the data. It's pretty easy to add and subtract with signal strength, like I showed off in a previous video. The big problem was the gaps. How would I successfully separate different numbers when there was a gap between them? As a first thought, I figured I would just take the intended state of each cell, move them all to the end of the row they were in, and do a bunch of funky data processing stuff all the way over there. Fun fact, this is not what I ended up doing. While attempting to do this, I found it was very annoying, and I had the thought to do it across the entire back instead. That way I would have more space to work with, and I didn't need to worry too much about moving the signals around and remembering which signal was which. I would just need to make sure that whatever module design I came up with for processing the data along the way would fit inside of the same 7 by 7 restriction as everything else. While I was deciding this, I was also thinking about how I would actually go about processing the data, and I came up with an idea. I could use 3 separate redstone wires, or tracks as I was thinking about them, to communicate which numbers go where. I could start at the opposite end of the board from the numbers, adding 1 to the final strength of one track for each filled cell, and then when I come to a gap right after a filled cell, I could switch which track I'm adding to. Then, at the end, I could feed each track into its own number display, making sure the first track being subtracted from corresponds to the rightmost number, the second corresponds to the one left of that, and so on. It was a sound plan in theory, but for a more solid blueprint of what I would actually do, I would need to test it out. I grabbed some brown wool and started with a quick mock-up of the 3 tracks, each one starting at a maximum signal strength and having the option to subtract from each of them by moving a block between a composter and a comparator. This subtraction will turn into the addition I want a little bit later on. I hooked all of these pistons up to a long red coder, meaning only one of them would be active at any given time, based on a fourth signal that controls which track is active at any given time. Then I made it so that the composters could be pushed out of the way of the comparators if the cell's intended state was not on, so that if the cell wasn't in the solution, it wouldn't add to any of the tracks, no matter what. This method caused some problems with the comparators not updating, but adding in some extra pistons fixed that pretty easily. After some testing, the system seemed to work, so I started to build them into the main Picross board. Then I needed to be able to mess with the control wire, which only took some basic logic gates to figure out. Finally, at the end, by the numbers, I resubtracted the tracks to turn all of the previous subtractions into additions, added 2 to account for the display being a bit funky, and watched as my rows were automatically updating the numbers on the side, just like I wanted, accounting for gaps and all. The displays closer to the end were showing 0 instead of blanking out, but that was an easy fix. I just had to mess with the signal strength if it was low enough and turn on the manual override that I put in place for, you know, this exact purpose. And it worked. It worked just like I wanted. Now I just had to get the column numbers working. Luckily, this wasn't very hard at all. I had already found a system that worked for the rows, so I just had to make it orange and adapt for it to work vertically instead of horizontally. This mostly just meant changing the tracks and the control line from straight wires to upward spirals of dust and comparators. This works just fine, but it does come with the unfortunate side effect that it's significantly slower than the rows. I don't mind it all that much though, because it does give me a good chance to rush around to the front and enjoy watching the numbers update. I think I find too much joy in watching this happen. And with that, I had built a fully functional and programmable Picross board in Minecraft using a ton of redstone, a ton of space, and more than a fair amount of brainpower to figure it all out. And that is my latest behemoth of a redstone project. This was a massive project for me, by far the biggest thing I've made with redstone, so I really hope you enjoyed the video. I'm really happy with this thing. Seeing the numbers light up for the first time made me legitimately giddy. The only complaint I have is that 5 by 5 is not a lot of space for interesting Picross puzzles, but a lot of the systems that I made seem like they should be fairly scalable, so in theory, the stuff could potentially be used to make a 10 by 10 with only some minor adjustments. Apart from the number displays, those would need to be entirely redone. On another note, sorry for not being especially active recently. I've been busy with other stuff on my mind, like finishing up college semester, so I haven't had as much time to work on videos. Summer's coming up though, so I should hopefully be able to do some more stuff on this channel. I got some plans for a more building focused video. Hopefully there's some interest for that. Otherwise, I'm open to suggestions, so feel free to discuss. Anyway, I'm all done here, so have a good day and have fun doing some redstone.